Okay, the second application we're looking at in this section is balancing chemical equations. And in case it's been a hot minute since you took chemistry, or if you've never done balancing of chemical equations, the basic idea here is they give you some molecules that react and produce some other molecules, but they don't give it to you in the right proportions. And your goal in balancing this equation is to sort of say how much of this reactant and how much of this reactant will combine together to make these three products over here. And your goal is to find numbers, usually whole numbers, that describe how those will react. So in this particular case, we've got limestone and the acid and acid rain that combine together to make water, and calcium and carbon dioxide. But notice at the moment on the left-hand side, there's like 3 hydrogen atoms. And on the right-hand side, there's only 2. So again, these aren't combined in the right proportions right now. It's not 1 to 1 mix 1 to 1 to 1. So what we need is some multiple of that and some multiple of that. We'll make some multiple of that and of that and of that. So we need the amounts that go in each of those spots. So the way that I like to organize this, well, let's talk through it and you'll get a little more efficient maybe as we do a few more of these. But the basic idea is I like to write these in vectors. So describe each one of these molecules as a vector in terms of each of the possible atoms. So there's hydrogen, there's oxygen, there's calcium, and there's carbon. I'm just writing them down in the order I see them in the equation. It doesn't really matter as long as you're consistent. So our first reactant is 3 hydrogens, 1 oxygen, no calcium, no carbon. And we're going to need x1 of that plus x2 of the next one, which is 1 calcium, 1 carbon, 3 oxygens, and no hydrogen. And that's going to equal some amount of water. So 2 hydrogens, 1 oxygen. Plus some amount of calcium, which is just, let's see, 0, 0, 1, 0. And some amount of carbon dioxide. So, see, no hydrogen, 2 oxygens, no calcium, 1 carbon. Okay. There's the same equation I'm trying to balance, written in vector form. This is a system of linear equations. Again, normally we like to see our system of linear equations with all the variables on one side. So really what I would want to be doing is subtracting these 3 terms over to the other side. I think maybe I'll just jump straight to writing down the augmented matrix, if you'll allow me to jump that far. So the first vector in the matrix, in the augmented matrix, would be 3, 1, 0, 0. The next one would be 0, 3, 1, 1. When I move this vector to the other side of the equation, the 2 and the 1 become negative. So negative 2, negative 1, 0, 0. You could look at that as having a negative x3 on it, and just remember that when you solve for x3 it's negative, but I prefer to just actually change the constants so I don't have to remember that my x3 answer is supposed to be the negative of what I actually get when I solve the matrix. Okay, moving the next vector to the other side becomes 0, 0, negative 1, 0, and the last one to the other side, 0, negative 2, 0, negative 1. And keep in mind when you do move everything to the left-hand side of the equation, there's nothing or 0. So I'm going to just put a row a column, excuse me, of zeros. On the other side, I've got another homogeneous system of equations, augmented matrix with zeros on it. And when I solve this, I will get the amounts x1, x2, x3, x4, and x5 that balance this equation. It may be that they come out as decimals, and I may have to multiply by some constant to get into whole numbers, but let's find out what happens. Okay. So I've got the system typed into my matrix calculator here, and I double checked it for typos, I'm pretty sure, so let's go ahead and crunch. There is the RREF, the reduced row echelon form. And keep in mind now that this is x1, x2, x3, x4, x5, and the equal sign. We do have a free variable here, so as we start to write these equations back down, the first one will be x1 minus 2x5 equals 0. And I know I'm going to eventually want to solve for x1, so actually maybe let me start again. Let's go up here. So x1 equals 2x5. Let's see if we can get the others in a similar way. The next one says x2 minus x5 equals 0. And again, when I solve that for x2, we get x2 equals x5. I'm going to write down the other three just up here in the top right corner without writing down the other form. So the next one is x3 equals 3x5. And x4 equals x5. And there was no row for x5. It's a free variable, so x5 equals x5. And if you factor the x5 out of all of this, you get 2, 1, 3, 1, 1. Times x5. So there are infinitely many solutions to this system of equations, but all the solutions come in the same proportions. x2, x3, and x5, x2, x4, and x5 need to be the same size. x1 needs to be twice as big, x3 needs to be 3 times as big. So if I chose x5 to be 10 for some reason, I could do 20, 10, 30, 10, 10. There's no reason not to make x5 just be 1. But this is the point where if some of these were fractions, like if we got a 2/5 here, then I would choose x5 to be 5 to clear out the fractions. But in any case, at the moment, we have a solution that says, here, let's erase some of these. That says 2 of this, 1 of that, should make 3 waters, 1 calcium, and 1 carbon dioxide. Let's just check a couple atoms and see if this really works. Let's see. So now on the left-hand side, we have 2 of these, so we'll have 6 hydrogen atoms. And on the right-hand side, we've got 3 of those, 6 hydrogen atoms. Looks good. Let's check oxygen. So there's 2 oxygens there and 3 more there. So a total of 5 oxygens on this side. There's 3 oxygens there and 5 there. 5 oxygens on that side. I'll leave it to you to check calcium and carbon, but I think those 2 work as well. And usually after you've done a couple of these, you can get pretty good at just starting with the original equation here and probably jumping straight to writing down the matrix that you would need to put into your calculator. So you can get the solutions pretty quickly. It's definitely faster in my mind than just sort of the guess and check that they leave you with in chemistry. Or at least when I took chemistry, that's what they left me with. So probably simple chemical equations to balance this is overkill. But if it's a little more complex, this is a nice way to take advantage of the power of linear algebra and let it do some of the grunt work for you so that your brain power is free to do more complex things. All right, we'll look at one more application in the third video.